we can start now. It's 3 p.m. So now we are in the week 9 of this course, Introduction to Material Science and Engineering. And the list of the content that has been covered are listed over here. So in this particular week, for example, last week, in the week 8, we majorly talked about the diffusion. And diffusion is one of the most important factor, phenomena, which will govern the phase transformation. So without diffusion, phase transformation cannot happen. Okay. So now we are in the week 9. We discuss about the phase transformation. Then we discuss about the how the once a phase start to transform, first thing will happen like the nucleation should start. So the process of nucleation we have discussed. Good afternoon, Omkar. Next we discuss about the nucleation and the capillary rise. So they both resemble in a way. And we saw what are the similarity between them, the way their behaviors are. Then after that, nucleation, growth, and overall transformation. These three factors we have discussed, and we got that in the nucleation and in the growth, in both of them, the diffusion is required at high temperature and the low temperature. For example, our transformation is from the liquid to the solid. At high temperature, the nucleation rate will be slow, and at the low temperature, diffusion will be very slow. So the nucleation still will not take place efficiently. We got to know that as we keep on decreasing the temperature, the driving force is increasing, but the what we can say that the diffusion is decreasing. So somewhere in the middle, we got to know that the nucleation rate is highest, and then it again further decreases. Similarly, for the growth also, we got to know that the growth rate will follow this type of kinetics. The maxima in the growth is at the high temperature. This is the temperature axis, and the maxima of the nucleation rate will be at the temperature lower than the growth temperature. Then we discussed in detail about the TTT diagram, time temperature transformation diagram, where the start and the finish of a particular phase, we have discussed that. Later on, we discussed two type of nucleation process. One is the homogeneous and another is a heterogeneous nucleation process. Okay. Then we discussed about the heat treatment of the steel, where like we discussed that normalizing, annealing, quenching, or tempering. Okay. So this type of heat treatment we have discussed. Again, the week 10, like the entire transformation is not like entire heat treatment process has not been covered yet. Couple of heat treatment, for example, tempering and all, that will come in the week 9. So it is again this particular thing will be continued in the week 10. So these are the list of the content that we have covered in this particular week. I would like to ask you, like, if you have any doubt in the content that has been covered, please let me know. Also, if you are facing any difficulty in the assignments of the previous week, that also you can discuss with me. If there is any doubt, please feel free to text in the chat box. If you are comfortable, please you can also unmute and interact with me. Okay, since there is no doubt, we can move ahead and solve a couple of questions. So now, in this particular week, the majority was the conceptual thing. So I designed the question in that way. Questions will be easy. It's just that today I have more number of questions to demonstrate you. Let's start with the question number 1. We have to do the measure pair. Liquid to gas transformation, which one will be gas to liquid, solid to liquid, and liquid to solid. So very easy, right? Can you please, what about the liquid to the gas? Which one it will connect with? Vishnu, Omkar, any idea? Like if the transformation is from the liquid to gas, So will it be freezing, evaporation, condensation, or melting? B, right? Very good. That's the evaporation it will be. So Karan has answered. The option A is the right answer over here. What about the gas to the liquid? If we are going from the gas and going to the liquid part, then it very good. It's a condensation. Solid to the liquid, we have option D, right? Great. It's a melting. And then when we are going from the liquid to the solid part, it's nothing but the option A. So if you see the assignment, the first question of the week 9 is related with this question. It's the fourth one. Okay, very easy question. You can easily solve it. So it is related somewhere over here. Okay, if any doubt, let me know. If not, let's move to the next part, question number 2. So all the questions are like this. It's very easy. Okay, let me hide so that we can solve one by one. A phase transformation is a thermodynamically feasible only if the final phase has a higher free energy than the initial phase. No, very good. It's a false statement. If the final phase, let's say GF I am calling, initial phase Gi I am calling, if it is more, then what it means that the delta G, the phase is which is final minus gives free energy of initial, it will be negative. No, it will be in the same phase, right? Okay, so if the final the gives free energy or the final should be lower. If it is more, then what it mean? It means that the delta G is positive, right? And thermodynamically it is not feasible. Thermodynamic feasibility we check by the delta G, which is final minus initial. Since it will be positive, so it's not feasible. That's why it's false. Very good. Let's move to the next part. Question number, the second part, option B. The driving force for the phase transformation is 0 at the melting point. Since we are talking about the melting, it means that we are going from solid to the liquid. So what is the driving force for the phase transformation? Is 0 at the melting point. Actually, the option is true. Let's see why it is. Okay. So this is delta G and this is the temperature. And our transformation is melting, so we can talk about the, let's say, transformation from liquid to the solid. Let's say this is of the liquid and this belongs to solid. What is this particular point? The point at which the G of liquid and the G of solid, they are equal. When we are talking from the liquid to solid transformation, it means that this is nothing but the temperature corresponding to this will be the melting temperature. This is nothing but a melting point. The intersection point is a melting point. What we got to know that at this particular point, if we are talking about the transformation, the thermodynamic feasibility, liquid to solid, like so G of solid, the final, which is final is a solid, minus G of liquid, it will be there. Since they both are equal at this particular point, so delta G is 0, and delta G is nothing but a driving force. So at this particular point, we can say the driving force for the phase transformation is 0 at the melting point. So, for example, you took the solid or you took the liquid. For let's say you're taking the liquid, and from high temperature, let's say this is the temperature axis and this is the melting point. Above this temperature is a liquid, below is a solid. You are coming from liquid to the solid part, but what you did, you stop at this particular temperature. Now, your liquid is not going to transform to the solid. It will remain as it is because it doesn't have any driving force. Driving force is zero. It will transform only when you do the undercooling. If you go to the temperature below the melting point, then the transformation will start to happen because it will have sufficient driving force to do so. Okay. So with that, we can say that option B, for B, answer is true. Let's go to the last part. Vishnu, if there is any doubt in this B part, if yes, please let me know. I will try to explain in the. Oh, great. Very good. Now let's go to the third part. The driving force for freezing decrease with an increase in undercooling. If we are increasing the undercooling, will the driving force will decrease? False, right? More is undercooling, it means that the temperature difference is more. Temperature difference, for example, here. Okay, we are talking about the freezing. So let's say this much. This is the liquid and this is the solid part. Right now, at this particular temperature, we have this much of driving force. Decrease the temperature, driving force is increasing. Decrease it even more, driving force will even increase. Okay. So more is undercooling. The driving force will be the higher will be the driving force. Okay. So with that we have solved this. So its answer is false. Very good, Vishnu. So it's a false, true, and false. So with that we have solved this question number 2. Any doubt? Let me know. If not, let's move to the next part, question number 3. What is the thermodynamic driving force for the phase transformation? A. The difference in the temperature between the two phases. Difference in the free energy between the two phases. Difference in the pressure between the two phases, and difference in the volume. Temperature, free energy, pressure, or volume. We are talking about the thermodynamic driving force. Option B, right? Very good. It's a difference between the gives free energy, the free energy that a system is having, no matter what transformation we are talking about. Okay. With that, we have solved this question number 3. It was very easy. Let's go to the next part, question number 4. What is the first stage of the phase transformation? If we want to transform a phase, let's say from the solid to the liquid, or let's say liquid to the solid, what will be the answer? What will be the first thing that will happen? Growth, nucleation, solidification, melting. Yeah, that's right, Vishnu. Option B is the right answer over here. It's a nucleation. Okay. So for any transformation, the first thing that will happen is a nucleation. Then it will be followed by the growth. When we are talking about the solidification and the melting, these are the processes. They are not the they are themselves is a phase transformation process. These are the way by which the transformation will happen. Okay, so first it will be nucleation will happen, then it will be followed by the growth. Very good. Let's go to the next part, question number 5. What is the critical radius in the nucleation? We talked about the R star, which we note down that it's a 2 gamma divided by driving force, that is delta G. Right. So this is what? This is the critical radius which we are talking about. Now what does it mean? The radius at which the free energy change is minimum, the radius at which the free energy change is maximum, at which the free energy change is 0, at which the surface energy is 0. The right answer, very good. The answer is free energy change is maximum. Okay. So after this, so see what will happen, that it's a radius at which the free energy change is maximum. So we have found that this is a radius and this is a gift free energy. So what was happening is something like this. And this is the critical radius R star we are talking about. If my nucleus, which is formed, the size is R is less than R star, what will happen? Let's say, what will happen to the nuclei whose radius is this? What will happen is that they will dissolve. They are not stable. And what about the nuclei whose radius is more than r star? That is somewhere over here, let's say. In that case, they will not dissolve, they will grow. And they are stable nuclei. Right? So anything which is lying over here, they are not stable. Anything which is lying above this R star, it is stable. And after this, the growth will be followed. Clear? This is the significance of the R star. Very good. Let's go to the next part, question number 6. What happens if the radius of the nucleus is less than the critical radius? We just now discussed. So we can quickly answer this part. It will grow, it will dissolve, the free energy change will decrease, the free energy change will increase. The right answer will be the nucleus will dissolve. Right. So this is the thing which we have discussed, that over here they will dissolve. But if we talk about the one which is greater, then they will be stable and they will further grow. Yeah, very good, Vishnu. Option B is the right answer. Let's go to the next question, question number 7. It's a Mather pair type. 1, 2, 3, and 4. Nucleation. Increasing the size of the nuclei, initial formation of the new phase. Very good, option B. Nucleation is the initial formation of the new phase. Growth. It's option A. Perfect. Critical radius. Perfect. And then the last is state self, right? Great. Surface energy, energy associated with the solid liquid interfaces. It's option D. Okay, let's move ahead. Let's go to the question number 8. What is the driving force in capillary rise? We discussed that capillary rise is there, and for example, if I take a tube and I submerge it in the water or some liquid media, what we usually see that there is a sudden option A, the gravitational potential energy. So we are talking about the driving force, right? Some energy will decrease. Driving force means that there is a release in the energy will release. If we are talking about for example, gravitational potential energy, so initially, let's say the case 1, where the water was like this, there was no capillary rise. The center of mass of this particular thing will be over here. Okay, so m g h. In this particular case, what will happen, that certain amount of liquid, here the capillary rise is there, has went up. So now the center of mass will obviously shift from here to the above, if we are talking about the entire system. So here mgh star will be higher, so it means that this is energy increasing. So this cannot be the driving force. Right? Surface energy reduction, volume free energy, nucleation energy. The right answer is option B. What it means that, see, initially over here, what is the interface at this particular point, if I am talking about at this particular interface? So this is my this is my solid phase, for example gas, solid phase, so for example glass, and then there is a gas. So the interface is governed by the solid and gas interaction. Now what will happen once this liquid has formed over here? The interaction is no longer solid and gas, it's between the solid surface and the liquid. Okay, so if this surface free energy, if this is more than this, then this the rise will happen, the capillary rise will happen. So what is the driving force over here? The reduction in the surface energy. Surface energy initially was higher, now it's lower, so the reduction is happening in the surface energy. Okay. Volume energy is same, right? So option B here will be the right answer. Is it clear, Vishnu? Great. Let's move to the next part, question number 9. True and false. Okay, I have this. The critical radii R star in nucleation correspond to the minimum in the free energy curve. False, right? It's correspond to the, we discussed that, it's correspond to the maximum. Next part, the opposing force in the capillary rise is the volume free energy. What is the opposing force over here? What we have saw that the energy mgh is increasing. The energy increase, the gravitational potential energy is increasing. So opposing force is what? This is the opposing force, okay. So we can say that it's a false and it's a gravitational energy. Okay, so it's a false again. Let's go to the last part. The surface energy term in the nucleation is proportional to the R cube. Surface energy term in the nucleation we are talking about. R cube? No, the answer is not. It's a R square. The proportionality is R star, R square. Surface we know, right? Surface will be if we are talking about the sphere, let's say, the surface area will be given by the 4 pi R square. While the volume part, it will be given by 4 by 3 pi R cube. This is the volume part and this is the surface part. Okay, so we easily know that it's a R square, it's not the R cube. So again, this is the false, right? Any doubt in this, please let me know. If not, let's move to the next part, question number 10. So 1/3 of the questions we have covered till now. Couple of more questions are there. This is a very interesting part, and this type of questions can be asked in the exam. What is the unit of nucleation rate? We are talking about the nucleation rate. Option D. Option B, right? Per meter cube per second. So nucleation rate is number of nuclei per unit volume and per unit time. So number, we are not giving any unit over here. So it's a 1 over volume. We know that it's a meter cube and the time is second. So meter cube inverse and second inverse. That's the option B is the right answer. Very good, Vishnu. Let's go to the next part, question number 11. This is also similar type of questions. What is the unit of the growth rate? We have meter per second, right? It's like at what rate the things the nuclei is growing. That's the option A. It's a distance per unit time, meter per second. Very good. Okay, at what temperature is the nucleation rate? Okay, I thought this question has been asked in the assignment, but it's not. Okay. At what temperature is the nucleation rate is 0? Absolute 0, melting temperature, room temperature, critical temperature. the right answer here is option A, right? Absolute zero. But also, when we talk about the melting temperature, for example, our transformation is from the liquid to the solid, and liquid has to transform to the solid. What is happening in the, if we are talking about the melting point? At the melting point, the nucleation rate, does it have any driving force? So the driving force for the nucleation is G of liquid minus G of solid, let's say, sorry, solid minus liquid, final minus initial, and which is 0. It doesn't have any driving force. So this will also be counted over here. Okay, I should have used the word R. So A and B both are the correct answer over here. So at the absolute 0, why absolute 0? The diffusion will be 0. At absolute 0, when we are talking about the diffusivity, that there will be no diffusion because the atoms will not have any mobility at that particular temperature. Okay, when we are talking about the absolute 0. So A and B both is the right answer over here. Any doubt in this? Let me know. If not, let's move to the next question, question number 13. Question is here. What is the relation between the temperature of the maximum nucleation rate and the temperature of the maximum growth rate? Okay, nucleation rate and the growth rate. When we were discussing the option B, right? Very good, very good, perfect. So we saw that the growth rate will be like this, nucleation rate will be something like this, and when we on the y-axis it's the temperature. So growth rate is at the high temperature and the nucleation rate will be the lower temperature, maximum of the nucleation rate. So option B is the right answer over here. Great. Let's move to the next question, question number 14. What is the shape of the curve for fraction transform as a function of the time? Fraction transform as a function of the time. Linear, exponential, S-shape, parabolic. When we plot the fraction transform x as a function of the time, what we usually see, it is followed by something like this, right? This is a fraction of the transformation. For example, if you are talking about the liquid to the solid transformation, initially the transformation will be weak. Why? Because the nucleation rate will be very slow. Later on, also it will be the growth has happened to the larger extent. Now they will start to impinge each other. So here also it will be slow. In between, we have saw that in between the rates are high. Okay, if we combine both of them together for the fraction transform, it will look like this. We have saw in the class. So it will be somewhere in the middle, and they will take the maximum value. Okay, so the curve shape is like a sigmoidal S shape. So the option C here is the right answer. Okay, so we discussed the question on the nucleation, we discussed on the growth, and then we discussed on the fraction transform also. These are the three questions which is very important. One can also ask the unit of the fraction transform. So we already know that the fraction transform will be nothing but the rate of the fraction transform. Okay, it will be second inverse. Any doubt in this? Question number 14, let me know. If not, let's move to the next part, question number 15. So we have covered around 50% of the question that I have to discuss today. Very quickly we'll be able to finish the entire part. Any doubt in between you are facing, any questions you have, please let me know. What is the primary reason for the initial slow rate of the transformation? We talk about the transformation. was followed by this. Initially, the rate of transformation is very slow. At the end also it's slow. But it's asking why the initial rate is very slow. High atomic mobility, high nucleation rate, low number of nuclei, high growth rate. Which one will be the right answer among this? Okay, so initially, what will be the, so what do you think? What will be the right answer over here? Low number of nuclei, right? Very good. It's option C is the right answer. Perfect. Okay, great. Since we have discussed the similar type of questions, and now like we are very comfortable with the questions that that we are covering. What caused the slowdown of the overall transformation rate toward the end of the transformation? Increase in the nucleation rate, increase in the growth rate, impingement of the particle, increase in the atomic mobility. This is something which we have discussed. Why at the end the transformation rate is very slow? At the end the transformation is slow. The reason is that the growth has already occurred. So now one particle is impinging other to grow further, right? Here. So this particle, let's say particle 1, it's not allowing particle 2 and 3 to grow in further in these directions because it's impinging. So impingement of the particles are there. Okay, very good. The option C is the right answer. Perfect. Let's go to the next part, the question number 17. What does the nose of the TTT curve represent? This is very important. Time temperature transformation curve we have saw. It look like something like this if we are drawing the starting point, and if we are talking about this. Okay, so at this option A, maximum transformation rate, minimum transformation rate, start of the transformation, the end of the transformation. The nose, very good. Option A, the maximum transformation rate. So we are getting at this particular temperature, at this particular nose, when we are talking about the nose, the transformation rates are maximum, which is related with how the fraction transform. Okay, so this curve and this curve, they resemble with each other in a way. Okay, here the rate is maximum, fraction transform with the time. So here the starting point, since the rate is maximum, the starting point will be much more faster, much more, it will come, and the end point also quickly it will come. So the nose, it's the maximum transformation rate. Okay. Any doubt in this? Let me know. If not, let's move to the next part, question number 18. What is the result of very fast cooling in TTT diagram? Okay, this is something which we have discussed in the class. Glass formation, right? Very good. Like Martin-Cittig transformation or glass, like if you are talking about the metals, if you are quenching it, it's something like the glass is being formed. What it means that the liquid, we know, liquid doesn't have any symmetry and long range order it doesn't have. We are cooling liquid so fast and making it solid. The solid is in this process, the system was not able to take the shape. For example, if we are talking about the iron, it's not able to take the shape of the FCC or BCC. So whatever the shape was there for the liquid, it will form the same shape, and that's what we are calling it's the glass formation, because glass doesn't have any order, right? It's also amorphous type. So the option C here is the right answer. So if we are quenching, we'll get the glass formation. Match the pair. 1, 2, and 3. Slow cooling will give the fine grain, coarse grain, glass formation. Oh, very good. It will give the coarse grain. Fast cooling will give us the fine grain, and the quenching will give the lead to the formation of the glass. Perfect. Let's move to the next part, question number 20. What is the key difference between the homogeneous and the heterogeneous nucleus? Homogeneous and heterogeneous. Homogeneous nucleation occur on the surface, heterogeneous in the bulk. Homogeneous nucleation, bulk, heterogeneous surface. Homogeneous is faster than the heterogeneous nucleation, and heterogeneous required more energy than the homogeneous. Option B is the right answer. Perfect. So homogeneous usually start in the bulk. It doesn't need any defect or it doesn't need any surface. While heterogeneous, it will need a surface. Okay. So sometime what happen if I need to intensify the rate, the kinetics of the solidification, let us say, of certain particular phase transformation. Sometimes we add small little bit amount of the impurity in that, and those impurities will act like a surface and lead to the support the heterogeneous. And we know heterogeneous is faster than the homogeneous, and so my kinetics will be enhanced further. Okay, so option B here is the right answer, and this has been practiced in many of the casting techniques. Great. Let's move to the next question, question number 21. What is the shape of the nucleus in the heterogeneous nucleation? Sphere, spherical cap, cube, cylinder. Very good. Option B, it's a spherical cap. So if we have the surface, it will be like this. If I try to complete this entirely, so if the entire sphere, and then it's only the part of the cap type we are getting, only the part of the sphere. Okay. Option B is the right answer. Let's move ahead to the next question, question number 22. What is the relation between the critical radius for the homogeneous and the heterogeneous nucleation? Okay. Option C, yeah, R of heterogeneous will be equal to the R of homogeneous. Perfect. There is no difference in between them. Okay, it's just that for the heterogeneous, the driving force will be less. Delta G will be less than the homogeneous. For the same critical radii to form R star, for same critical radii, we'll get the, it will be like this. Great. Let's move to the next part, question number 23. Which microstructure is associated with the lowest hardness? The hardness is the extreme low. Fine perlite, coarse perlite, benite, martensite. Option B is the right answer, coarse perlite. If we have to arrange from the highest to the lowest, which one will be the highest? Which order they will follow? D will be the highest, then C, then A, and then B. Perfect. Very good. Right. With that we have solved. Martensite is the one which is the most hardest. Then in between, if I can add the option of tempered martensite, then the option, it will be lie somewhere over here. Okay, great. Let's move to the next part, question number 24. Oh, this concept of tempered martensite was not discussed, I think, yet. Okay, forget that part, last part. Huh. Question number 24. Remember. बंद कर दो. Option C. Okay. Not even read the question. Which heat treatment process involve the heating the steel after quenching to the reduced brittleness? After quenching to the quenching to reduce the bitterness. Very good. Yeah. Option C is the right answer. It's a tempering. Great. So if I have the martensite, which is like I quenched it, now I want to decrease its hardness. It's so hard, it's too brittle. So the process of tempering can be done, and we can reduce its hardness and we can reduce the brittleness. 25. I think I have 3 more questions left. The question says, What is the primary limitation of the iron carbon phase diagram in understanding the phase transformation? It does not include the carbon concentration, it lacks the time scale, it does not show the temperature variation, it does not include the alternate. Option B is the right answer. Okay, and for this only we have TTT diagram. So phase diagram can give us which phase can be formed. Again, it's the equilibrium phases. And the TTT diagram will give us the at what rate a particular transformation, in how much amount of time a particular transformation can be carried out. Let's go ahead. Let's go to the question number 26. What is the primary factor that determine the coarseness or fineness of the pearlite? Carbon concentration, cooling rate, heating rate, holding time. Very good. The option is B. We can take the, let's say we took the 0.8%, let's say, pearlite we took. We heated it, hold it, and then we are cooling down. The heating rate and the holding time, as long as the holding is sufficient enough that all the pearlite has been transformed to the martensite, the holding time is not going to affect, as long as the sufficient amount of time we have provided. The main thing is the cooling rate. If the cooling rate is slow, that is annealing, then what we'll get, the grain will be more coarser. The distance between the ferrite and the, like cementite and the ferrite layer, will be more. While the cooling rate is higher, for example normalizing, in that case we'll get the distance will be even more smaller. With that, you have solved this question number 26. Okay, two more questions are left. What is the primary reason for the C-shape curve in the TTT diagram? The balance between the driving force and the atomic mobility, the balance between the temperature and the time, balance between the carbon concentration and the temperature, nucleation and the growth rate. Primary reason for the C-shape curve in the TTT. So, what do we think? Nucleation and the growth rate, driving force and the mobility. Option D. Okay. I think I made the question in the wrong way. Option D is the right answer, but I should have eliminated this option A itself to avoid the confusion. Okay, let's forget that option A is here. So option D here will be the right answer. So it's the balance between the nucleation and the growth rate. Okay, at high temperature we have the nucleation rate will be low, and then when we are talking about the C shape, at particular point we will get the high nucleation and the growth rate. Let's go to the last question. It is made up of the couple of questions. Where is my hiding part? True and false. The transformation time decrease as the temperature decrease below the eutectoid temperature. The transformation time decrease as the temperature decrease below the eutectoid temperature. If we decrease the temperature, the transformation time will decrease. It's true. The time will decrease. If we decrease the temperature, decreasing the temperature means that we are increasing the driving force. If we increase the driving force, then the kinetics will be faster and the time required will be low. Let's go to the next part. Option B. The driving force, the transformation of the austenite to the pearlite, is increase in the free energy. What will be the answer here? The driving force for the transformation of austenite to the pearlite is the increase in the free energy. Answer is no. For any transformations, the energy will obviously decrease. Then only it will happen. Okay. So with that, it's option. It's no. Let's go ahead to the next part. The primary factor that determines the coarseness or fineness of the perlite is the cooling rate. That's what we have discussed. Yeah, very good. It's a true. Last one. The TTT diagram is used to understand the time required for the phase transformation. So these are the list of the questions that I wanted to cover. So 28 questions was there, but we were able to cover in I think only 45 minutes. That's great. So before we wind up, I would like to ask you, do you have any doubt in the list of the content that we have covered till now? So why the full annealing or the yeah, question is that why full annealing for hyper-eutectoid steel is done between the ACM and A1. Let's open the TDT diagram for the hyper-eutectoid steel. This is something which is going to be discussed in the week 10, but still let's have a quickly, we'll have a look on that. Hyper-eutectoid hypo we have here, and then we have, there is a hyper. This is eutectoid. See, these are the videos which we are going to cover in the next week, but we'll just have a look on the graph which is made by the professor.
So here,
This is the percent less than 0.8. Okay, this is more than the 0.8. No, so finally we have. So now let's see the question: why the full annealing for the hyper-eutectoid steel is done between the ACM. This is over here and the A1 over here. So now, for example, this is my austenite phases there. In the case of full annealing, what we want to do is we want austenite to be there, and then we rotate it. Is the question is correct? I'll do one thing. I have to go with this particular video first. I think once the professor has covered this part, then I'll be able to answer more effectively. Why the full annealing? Full annealing means mm,
protector Fe3C.
okay. I'll go through this concept and I will get back on the in the next week. The week 10. This concept has been covered, so we'll discuss it that particular point. I will once I quickly get the question, once I am able to grasp the question very quickly, then I will also try to respond in the Q&A forum. Okay, so please have a look onto that. Maybe by the end of tomorrow I'll be able to answer. I will put it in the dot solving forum. Okay, any other doubt on this? Full handling for the hyper-eutectoid steel is done between the ACM and the A1. ACM and the A1. There was a reason, I think the cementite, the problem is with the cementite somewhere, I think. While the full annealing of is done somewhere over here of this and this. Okay, I got the question. I think there were the multiple processes in the full annealing and the normalizing. So, but I'll go with the definition first. Maybe I forget that part. Okay, I will try to respond to this in the upcoming week. Okay, Vishnu, any other question regarding whatever we have discussed now in the week 9 or before that? Yes, please. Okay, seems like there is no question, so we can wind up today's class, and I'll get back to you like in the week 9.